Hello everyone. I'm gonna give a talk, as Professor Zhou mentioned, on topic of Vetaverse, which we recently proposed as a paradigm, as how we envision the future Metaverse will be shaped like for particularly vehicles and the transportation systems. So the V obviously represent the vehicles. So yeah, I'm Pengyuan from USTC, and I'm currently working on related topics. So yeah, let's dive into it. So, okay. So yeah, I hope you are viewing the correct window, because I'm currently using two monitors, and if anything, any issue came up, please inform me. Yeah. So this is how we uh, vision the future Metaverse could be consisting of. So we majorly cut it into two phases or two components. One is the intro vehicle, so what's inside each individual vehicle, and well, for instance, those rich media informational, and how we can render AR and VR information on the window shield, or using AR or VR glasses wear by the drivers and passengers. So anything happened inside the vehicle, but powered by Metaverse applications and techniques. That's the first component. And the second component that we want to go beyond each individual vehicle is to further to push the Metaverse into connected vehicles, or even bigger, the entire smart city transportation systems. So what we call it is the transport system Metaverse. So in these components or this stage, the focus shift from like individual vehicle performance to the interaction between the vehicles, or interaction between the vehicles and the roadside units, or in general with the cloud. So yeah, that's the two stage or two components that we envision the future Metaverse could be consisting of. And obviously, we need a stack of technologies to enable those interesting and exciting applications. So the bottom is the digital twin, which is the fundamental of how we build all this kind of stuff in a virtual world, so that we can monitor all the details. And eventually, we want to also not only moving everything different from physical world to virtual world, but reversely, we want to provide a reverse control function for the maintainer or the administrator of the digital twin platform, so that, for instance, if we want to change something in the reality, for instance, some maneuver behavior of any specific vehicle, or in general, we want to change some behavior of roadside units, for instance, we can just do some tricks in the digital twin platform, so that control can be in real time reflected in the reality. That's the eventual goal that we want to realize with the Metaverse platform. And then we can go upper to the stack. So there are 3D modeling, point cloud map, edge cloud, all this kind of stuff that we need to realize this real-time interaction between the virtual world and the physical world of the Metaverse. And obviously, in the middle layer, we need some advanced networking technologies, like currently 5G and the coming 6G, to make everything communicating in a faster way and more efficient. And on the upper layers, we have this kind of like audio or video algorithm and techniques to enrich the media with augmented reality and virtual reality, or even 3D point cloud streaming, so that the user can watch more kinds of format of videos or images than current cyberspace that we provide, which is basically mainly 2D plain images or videos. So that's our overall take, overall outlook of the future Metaverse. And yeah, let's see. I would, because the time is quite limited due to this, I think it's half an hour, so I will skip some details and we can just look at the big pictures. So yeah, so now currently, both the academia and the industry related vehicles are focusing on providing a more enriched media. For instance, in this case, we can render some AR information on the window shield. Of course, there's no really window shield scale of AR HUD these days. Mostly we just put a small mirror in front of window shield and then reflect that the AR content onto it so that we can see what's beyond the real background that the drivers can see. But still, we need a small head movement. Although we don't need, the drivers don't need to totally move down their heads, but still the information is not on the window shield itself yet, so they still require a small head movement to see the entry menu. But what's beyond this kind of stuff? So because now everything is still restricted to each individual vehicle's vision radius. So what it means is like these things. So nowadays ADAS or any self-driving or so-called self-driving high-end vehicles like Tesla are equipped with a bund of a number of advanced sensors and cameras surrounding the vehicle so that the vehicle can see everything beyond surrounding the vehicle, but only within the line of sight. So if there is obstacles can severely limit the vision radius of each individual vehicle. So what we want to achieve with the Vetaverse is that we want to achieve something like this vision from the Captain America movie, the second one, the Winter Soldier, so that we want each vehicle can see beyond its own line of sight to see what the drivers can't see with his or her own eyes. So that can only be achieved if each vehicle and the nearby road units can talk with each other and share with them what they see. So that each like if I'm driving a vehicle, the AR HUD not only tell me what I can already see or the cameras of my vehicles can sense. It can also render something that's beyond my line of sight. So because the vehicles or the roadside units or the cameras surrounding the vehicle, they can send what their vision to my vehicle so that my vehicle's vision is further extended, like in this stage. And this kind of accident actually happens a lot. So for instance, these two accidents are quite common in reality, and they both occur because of lack of vision, because there are some obstacles like the corner of the intersection, or the left one is there's a big truck preventing the driver seeing there is something other on the other side. So if those vehicles can talk with each other, both of those accidents can be avoided with the extended perception, so-called. So that's why we proposed back to 2020 a edge facilitated extended perception framework for the AR HUD. And the idea is quite straightforward, but it requires a lot of detailed consideration and improvement. For instance, if let's say there would be quite some years before every vehicle become fully self-driving or fully equipped with a powerful GPU. So there will be some years the road will be mixed with high-end vehicles like Tesla, but also ordinary vehicles without powerful GPU. So those vehicles will become the bottleneck of this extended perception vision, because they don't have the equipment to process these image tasks in real time, right? So they can't even do the simple object detection task. So how can they share the dangerous objects with the surrounding vehicles? So those vehicles would require some edge or cloud offloading services, obviously. But the cloud, as you may know, is a bit too slow for this kind of real-time connected vehicles applications, which normally, according to the standards, require below 100 millisecond inter-vehicle communication. So edge offloading obviously is a better solution, which can provide faster offloading and also robust performance. Considering in the peaking hour there could be a faster increasing demand for this kind of offloading vehicles, so that we can disseminate the peaking hours demand into the distributed edges. Then a question. I'll skip the details of the framework, and we also deploy this with real vehicles in the city center of Helsinki in Finland, and it works quite well. And it indeed provides much faster communication and offloading services compared with using a local cloud or even remote cloud. But then a technical question is how to properly select the best edge server in the surrounding in real time. And this is non-trivial because we not only to consider the communication cost, but we also want to select a edge server that can best perform in regarding of the queuing length and the available resources. So I will skip the details of this distributed. In the world, we use a distributed algorithm to select the edge cloud without using a normally central coordinator to select the cloud. So the edge server, in a sense, they can vote by themselves and without too much communication additional cost. So then in that way we can choose a edge server best performance in near real time for the offloading services. But meanwhile, during the development, we also noticed another issue coming up, is that when, for instance, in this case, so the right bottom figure, so we indeed let each vehicle see beyond its own vision by rendering some objects shared by another vehicles. But then when we increase the number of vehicles in this framework, we notice that there could be too many objects rendered on the window shield. So which becomes a new bottleneck of the perception system, because now instead of facilitating the driving experience, it becomes to block the whole reality vision of the driver. So the driver can only see all the shared objects rendered on the window shield everywhere, but the driver can't see what's in the reality. So how to properly and fastly to choose the most important object information from all these can be hundreds or even thousands of objects shared by all the vehicles and roadside units, especially in the city center area. So the information efficiency is a new challenge that we noticed from that work. So therefore, we continuously work on this topic, and based on some previous founded law. So for instance, there is a limited number of that one people can observe in real time, and the reaction and the cognition capacity can be severely impacted if go beyond that number of objects. So that gives us a scientific upper bound and the lower bound of how many objects that we want to share in each image frame from all the surrounding vehicles. So we need in the world, we need a very efficient filtering system to filter out all the less relevant information in real time and only render those most important things. So we propose this this AICP framework in last year. And the beauty of this algorithm or this framework is that it's unlike normal work, which focus on mostly application layer information filtering. We propose this as a full stack filtering framework, which can start the filtering mechanism from as low as a networking transportation layer. so that we can cut off the irrelevant information during the transmission, not only inside each vehicle, but during the transmission. So it is faster, and it provides a more efficient filtering mechanism than the normal filtering system. And of course, to do that, we need to propose our own transportation protocol stack, but which is also requested to be compatible with current protocol stack. So that's why we propose this VDU. Well, this is quite networking orientational work, so I will skip the details, but if you're interested, you can search the article and look at it. So in the world is fully compatible with current vehicle networking stack, so that it can be easily embedded into the industrial level products, and it allows a networking layer filtering during the transmission, so that we can cut off a lot of messages in the first 3 hops of the message transmission, which saves a lot of time for the application layer transmission. Application filtering. And to do the application filtering efficiently and properly, we defined our own model of the informativeness of each message. And this is quite messy, so I will also skip the details. Please check that in the paper. Yeah, so maybe one thing that I want to mention is that a lot of works in this regards use a machine learning algorithm, which is quite heavy for this kind of application. Not only the capacity required, but also the time to do the training and the inference, which is not quite suitable. So instead, we use this kind of like a metric learning. It sounds learning, but it's not. So we just train a very lightweight matrix, which can learn the correlation between the metrics that you define to rank each priority of each message. So it's very lightweight. It doesn't require machine learning on your network so whatsoever. So, and you can do a quite job in the end. So yeah, like you can see here, the performance is quite good, and it requires close to 0 additional time cost. So yeah. And yeah, that's our work and the road test. And so yeah, to sum up the previous stage, that's how we beyond each individual vehicle, so that we can let each vehicle talk with each other to extend their perception in the metaverse. And this not only can do the safety application, it can also for some entertainment application. For instance, nowadays a lot of factories are trying to bring up this kind of like connected vehicle metaverse platform, so that the drivers and passengers can see what other vehicles are doing or driving, where they're driving, or what they are trying to do, so that they can simulate themselves in the virtual platform to as a like car game. So with our platform, it can be easily achieved. And the next question we are interested is the privacy issue. It's quite hard recently. It started from as early as 2018 from Europe, the GDPR policy, and then USA now finally get into China since 2020. A lot of privacy regulations and laws are enforced these days to better protect user data privacy and security. So for Metaverse, we have more different kinds of data to protect in regards of privacy, because now we are not only using this plain data, we are also collecting a lot of this like a human related data, for instance, the eyeball tracking, or even the heart rate, how you walk, and of course the facial and stuff, they are already there. So we require more kinds of data to protect for the user benefit. And then I give one example in this regard is how to do the volumetric video streaming inside the vehicles from the cloud. The volumetric video, if you don't know, is a quite important component in the metaverse piece. because it can give you a fully 6 degree of freedom, so that the user can, browse inside the continuum of the video from different angles to different scenes. It's fully up to the user, so it provides a much more free experience than current 3D. But the issue is that it also requires much more volume of data to render the scene, and also of course to transfer if the video data is stored in a central cloud, which is common case. So how to do those kind of streaming in an efficient but also privacy preserving way is how we, I did another work which is well, currently we are doing several related works on this topic, and most of them are still unreal, so I won't give you too much details. But the core trick here is, instead of use the traditional reinforcement learning, we add a federated learning layer in the lower end, so that each vehicle or each client, they can aggregate their learning experience, but without uploading any raw user data like your Apple tracking data. That's not requested to be uploaded. Now each individual vehicle or each individual video watcher or video client, they only need to upload what they trained their neural networks parameters from the local end to the cloud. So basically none of the privacy issue can come up, because to reverse engineer that kind of neural network and even further the raw user data is quite difficult. Yeah, so yeah, it's a quite complicated framework, so I will skip the detail because it's not that relevant to our full course. Well, it performs quite well, as it outperforms a lot of quite famous SOTA, and yeah. So the takeaway I want to give from this topic is that we may want to put more attention in the metaverse or in general metaverse, because it requires a lot of psychological data, which can severely impact our user privacy. And this is a long gone issue in current web or in current networking or computer science society, because we didn't put much attention on the privacy in the beginning, and everything is added as it goes. So mostly in the later phases, and the later we put attention onto it, the more effort that we need to spend to make the privacy preserving techniques properly embedded into existing system. So we may as well, because Metaverse is not there yet, we may as well just put attention in advance, so that we can incorporate the consideration of the protection of the privacy mechanism in the beginning. Yeah. Okay, so as an integrity, yeah. So let's see this. So we are building currently a digital twin of a transportation system, but more in general a smart city, but focusing on the transportation system, so that we render everything from reality map data, and we import. This kind of platform is quite useful, as we can replay the historical realistic transportation data, but we can also generate some synthetic transportation data to to simulate the different cases. It can provide two use cases. One is that we can train the traffic light control systems with near to zero cost, because everything is in software and we don't need much computation power for this kind of stuff. Of course, if we do the scalability framework in a proper way. In a sense, the larger area that we want to put into this digital twin will require more computation threads in parallel. So how to do that properly is a distributed system question that we are currently working on. And the second use case is that we can do the autopilot driving algorithm training in this kind of stuff very easily compared to what currently the people are doing. For instance, using the real car, in a limited road segment to do the test, because that limit the cases that each vehicle can be met with a lot. And in this digital twin platform, we can simulate as any case that we want the vehicle to be met with as possible. So there's basically no limit that putting on the testing cases, so that we can train a autopilot algorithm with quite high robustness, and it can react to any possible danger on the road, and it costs nothing because we don't need any real driver or any road policy for this kind of stuff. We can just render anything that we want as long as it can be reflected in reality. So yeah, of course there's a number of quite challenging obstacles to tackle in this regards, because it's not only for instance 3D game that we want to build. But this is the difference between digital twin and 3D game, is that we need everything to be physically realistic. So we need a lot of, for instance, math knowledge and physical knowledge to know how to build each part of digital twin platform realistically. For instance, we need the wider condition, and we need the road physical feature to let everything run in a realistic way. And this is non-trivial, and it requires a cross-domain knowledge for this kind of stuff. But yeah, we are working on it, and so this is like a framework that we designed for this kind of digital twin. And in the end, like I mentioned in the beginning, after we have everything virtualized, what we want to do is not only to see what's in the reality in the virtual platform. We also want to provide some reverse control onto it, so that we can do this kind of stuff in the digital twin, but it can be reflected in reality in real time, so that we can cut a lot of manual efforts in that regard. And another benefit from that is that we can accelerate a lot of manual testing in that regard, because now we can test everything in the digital twin platform, and we can limit it how much area that reflection in the real world is, so that we can do a lot of different cases, different tests in the digital twin, but with very limited impact on the reality. So that's another benefit. I believe NVIDIA and Tesla and probably Xiaopeng, they're all doing that kind of stuff in these days. So, yeah. And yeah, that's my time for the talk. And if you are interested in this direction or related direction, here are several venues that we are hosting in the top magazine and the conference that you can submit. For instance, in this flagship magazine, in the Vehicular Technology magazine. So I'm leading this special issue on the Metaverse, so which is quite proper for this kind of submission. And you can check this copy paper with this QR code. And we're also hosting a number of workshops in this year, WiSATS, which is also relevant with Metaverse. So if you're interested, you can also check them out from the WiSATS website. Yeah, and that's my talk. Thank you.
Okay, thank you very much, Professor Zhou, for the exciting talk. Very insightful, and Metaverse, I believe it will be next big thing So
thank you.
as Metaverse becomes popular, yeah, I think it's a very nice idea to incorporate Metaverse into the Internet of Vehicles. Yeah, thank you, Professor Zhou. Okay, do you have any questions from the audience? Yeah, please take this opportunity to ask questions. Professor Zhou is the expert in Metaverse and Vetaverse, so please cherish this opportunity and ask insightful questions.
Hello, Professor Zhou.
Yeah, hi.
Hello, can you hear me? Yeah.
Yeah.
Thank you for your exciting presentation. And I have a question about the Metaverse and the MAR. I mean, it's real application. Can I ask your thoughts about the future application about integrating the Metaverse and the MAR, except for the vehicular or something? Do you have more expectation for the combination or some insightful thoughts about it?
Yeah, so currently most people are focusing on the AR HUD, so the so-called augmented reality head-up display. And I think it can be a practical application since, many people are doing it already. And of course, there are a lot of, issues to tackle. Like I mentioned, the information efficiency. So how to, avoid the overwhelming rendering on the window shield. But I think eventually they can be evolved. And I noticed another trend in this direction is that many industrial companies, they are now developing in-car AR applications, but it's not, it seems not that innovative because nowadays the solution are majorly, letting the passengers wear AR glasses inside the vehicles. So it's more like, to not proposing a new thing, but just to migrate the AR use case from outside the vehicle to inside the vehicle. But of course, there is new chances and new issues because now they want to integrate what the passenger see from the AR glasses with the surrounding road condition. So for instance, some companies developing this kind of like AR game so that the passenger can wear AR glasses and play an AR game on a simulated road, but the road is highly paired with what in reality the vehicle is driving around. So that's how people are doing this nowadays. I think they have some chances in the future if we develop it in a proper way. So yeah, that's my thought. Yeah.
Okay, thank you, Professor Zhou. So I think you possess a positive attitude to the combination of Metaverse and MAR in the future.
Yeah, I think it's quite positive.
Okay, thank you, Professor.
Okay, Professor Zhou, so maybe I ask a question. So okay, so for the AR or VR devices, are they wireless these days, or do they have a cable to be connected to the desktop computer? So I mean, what are the trends for the devices? Do you have any comment?
I think the AR glasses nowadays mostly are using or trying to use at least wireless communications, because the point of using AR is to enable the clients to wear it and to go anywhere without a cable limitation. And that's work quite well from my observation, or at least, for instance, our lab is using HoloLens 2 to do some tests, and it has no issue regarding the wireless communication. But for VR, it's harder as VR normally requires a larger volume of data in the transmission, because everything now in the VR is virtualized. In AR, we only virtualize some contents, but most of it, for instance, the background is still reality. So the data volume is much less than VR. So nowadays, VR, I think, is still limited to cable connection. And whether it would have wireless communication in general, or whether it requires wireless communication in the future, is something to find out, because an issue is that, or a difference for VR is that now everything is virtualized. So there is a safety concern that if the clients really go anywhere he or she goes, so maybe it's safer to limit the clients just inside the room or indoor at least. So if that's the case, then probably cable connection is good enough. Yeah.
Okay, thank you very much. So for your idea on Vetaverse, could you comment what the industry is doing? Is there any standard body trying to come up with some standards?
I think a lot of people are trying to propose some standards according to their own interests. But I guess in the end, like what other techniques developed, in the end, it's the big guy who says so. So because the market, who owns the market, who owns the standards, right? Because everyone else will just follow the market and follow the leader who lead the markets. So there can be a number of different standards in parallel, but if we don't have the market, then the standard doesn't make any change. So yeah.
Okay, thank you. I mean, so you have an exciting survey coming up. So is it accepted yet?
No, it's still under review.
I see. Okay.
Yeah.
So you discussed many different topics about Vetaverse. So for example, mobile edge computing, security, privacy, everything is inside.
Yeah, I think so. Yeah.
Okay. Very nice. We look forward to study your paper after it is published.
Yeah.
Okay, so we have a question from the chat box. Because he is not using microphone, so I just speak the question for him. He is asking, what is the most possible first step to implement or try the vehicles in the metaverse?
Yeah. So yeah. By the way, the survey is already on Arxiv, so you can. But of course, on the Arxiv is a longer version, so that can be better for the accepted version. So yeah, regarding to the question, I think the focus of the question is try to do something in the Metaverse more practical while catching eyes, right? So for that, I think doing some or developing some AR informational games or AR applications in car. So in other words, to let the clients or the passengers still wear something like AR glasses and to see AR or VR objects or AR VR games, but simulating the background of the AR or VR games or things, considering what the vehicle is driving. For instance, if we are driving in a city center area, and then if you let the passenger wear a VR glasses or AR glasses to play something or to view something, you can render the background as similar to the city center area that currently the vehicle is currently driving through, so that when the passenger when they want to see outside the glasses, they can feel a seamless, more or less a seamless experience, because inside and outside they are both having a similar background. So that can be something that's more practical to realize in this stage, and that can catch a lot of attention from at least industrial guys, because that's what I know what they are doing nowadays, because they think AR glasses compared or VR glasses compared with HUD, head-up display or window shield, is much easier on the much more practical way to realize AR or VR applications nowadays, because window shield is much harder to do, and glasses is much easier, and it costs much less. So I think, yeah, if you want to, if you are interested in this direction, probably do some, AR or VR game development inside the car, but still using the AR VR glasses. That's a way, yeah. Okay, so the next question coming up in the chat is what's the main difficulty in integrating fast learning with Vetaverse? Is there an efficient way to solve the dynamic selections of the vehicles, considering the fast movement nature of vehicles? Yeah, I think that's more like a networking problem. So in this regards, I assume the by default communication mechanism is through the cell stations, which is 5G or the coming 6G, whatever. But then the speed of vehicle, well, it doesn't really matter, because each sub area will have enough or sufficient number of cell stations localized. So any vehicle in any position can just connect to the best cell station for the fast communication. Because in this concern that using fast learning, we are only uploading the neural network model parameters. So the actual location of each vehicle doesn't matter, right? Because all those, regardless of the actual location, we are only uploading a aggregated parameters. And then each vehicle can connect to a best selected cell station, like currently what they are doing, because currently that's how the vehicle talks to the cloud. So the technique is already there, and we are just replacing the uploaded data from what now is raw data to the neural network parameters. So yeah, I think that's quite easy to solve, and we don't need much more efficient proposal to solve this question, because currently the handoff algorithm of the cell station is already good enough. But one thing that we notice is that if we want to upload more data than neural network model parameter, because normally the parameters are quite small, except if we want to train some like ChatGPT, like a large model, then that's another question. But other than that, normally the neural network is quite small in terms of data volume. So, but if we want to upload something beyond that, for instance, if you want to upload some AR content to the cloud, then or some offloading task to the edge of the cloud, then we need some consideration to improve the handoff algorithm, because now we not only to consider the communication efficiency, but we also need to consider the offloading efficiency. So how to choose a best trade-off between those? That's another question. We also provide some early stage answer to it in a 5G MEC handoff paper. You can check it also. Yeah.
Okay, thank you so much, Professor Zhou, and people who have asked the questions. So do we have additional questions from the audience? If not, I think we thank Professor Zhou very much again. So he's the top expert in Metaverse and Vetaverse. So so we are looking forward to study more of Professor Zhou's papers. So I encourage you to check out Professor Zhou's website and his publication pages to study his latest papers. So because he's pushing the cutting edge technology, the front end of this exciting Vetaverse technology. So we can all learn a lot from him. And thank you very much, Professor Zhou, for the very exciting and insightful keynote speech. Indeed very useful for our own research. Thank you.
Thank you, Professor Zhao, for the invitation and hosting, and thank you for the questions. Yeah.
Thank you. Okay.
Yeah.
So yeah, Professor Zhou. Okay. Yeah. Have a nice day. Thank you.
Yeah,
Bye.
you too. Yeah, bye-bye.
Bye.